Okay, so this was an introduction. Remember what we actually did last time, and that was um, the problem that we'll go through. We'll be getting back to it, and that's the mixture, the Kaplan mixture problem that illustrates the linear algebra, the issues that we're gonna deal with very nicely. And so we have previewed a bunch of them right now, and we know what we need to do before we actually proceed. And so what we are right now is the kind of a language of mathematics needs to be developed in order to for us to deal with the somewhat complicated issues when we move to the next level. Okay, so we spoke of logic already. Okay, so and now, so that's the solution. This is the logical implications. We talked about that a little bit. Okay, and so, and now we were to speak of sets. Hold on a second, did I click on the right one? Oh, I didn't click on the right one, but it's the same story, for better and for worse. Okay, so so to point out something more immediate that we're going to deal with is what is that we will be studying as the smallest elements of what we're studying are have been numbers, okay, and now beyond that there are points, maybe on the plane, maybe in high dimensions, okay, then vectors once again maybe dimension whatever 2 or 3 or higher, and then functions. Okay, so as you can see, so these are the smallest pieces that we make linear algebra from, and then but they are different enough among them, and so they have to be treated then in a uniform fashion, and that the uniform language of treating these different things is the language of sets. Okay, so to point it out, here we already have introduced, as you can see, we have functions here, we have relations, we have vectors, we have points, all of that have come up already. And now as we're moving on to actual, before we move on to actual linear algebra on the next level after this introduction, this is what we are confronting, different types of building blocks, and therefore that we prefer to speak of sets, relations, functions in the abstract context. So you've seen functions surely, but they have been almost entirely numerical. So a number input, number output. That's the whole calculus one. So even pre-calculus primarily concerned with that. That's not good enough anymore. Okay, so the inputs might be vectors, for example, output could be once again vectors. So not to dwell on that, how do we not dwell on that? The answer is ignore the nature of the inputs, outputs, and build an idea that is entirely abstract. So it doesn't matter the nature of those outputs. There we speak of then sets and their elements. Okay, so that's the most abstract way of dealing with that issue. Simplify, strip the structures that numbers, for example, have of the number set and deal with it as if it is there is nothing else there. Okay, so and then so that's the bad news. That's the hard part that we're dealing with in this class. And the simplifying part is item 2 here. We only will be dealing with relations and functions that are or likely to be linear. Okay, so not even quadratic. Okay, so that certainly is it simplifies things. Okay, so then it is a language. That's what this is. It is a language, a simplifying language. This for part 1, a simplifying language of mathematics. So you're looking at things that are distinguishable but not related to each other, if it makes sense. Okay, so numbers, remember, so once again, distinguishable, but not with no without any structure, without relations. So once again, what the relation between numbers could be: algebra. Number one, number two is geometry. You can measure distances, and number three is the order. So less or small, smaller, larger, and so on. Okay, so these three, one, two, three things that you can do with numbers are ignored if we speak of sets. And so whenever we need it, we bring algebra. When we need geometry, we need to bring geometry. And until we do, we ignore that altogether. Okay, so once again, what makes sets is just the elements are distinguishable, like a label attached to it. So once again, it is not uncommon to in mathematics or computing to call things by their names, and that's the only way to tell them apart. So the rest of the attributes might be ignored altogether. So to illustrate this idea, this is what when we speak of sets, that's what it might look like. So you have a structure, because wherever things come from, they might come with a structure such as numbers. Once again, in this case, there are marbles, and then they are arranged in a circle. So, but we don't care about the circle for the sake of this analysis, and so we shake the back. So to get rid of the structure that is just in the way, it is a distraction. So we just want to be once again to see what we have, what's on the right, because of the different colors. Those marbles are distinguishable, and each of them is separate from another, but otherwise they're not related to each other. So you can shake once, you can shake again, and so they're not close to each other in any way, and certainly don't interact in any other way. So it's a simplification through abstraction. So removing things that we don't care at this time. So have you seen this idea of sets before? So I'm not sure how it's done in computing, but this is the way it's done in mathematics. So it is only the structures are put in when we want them. It's entirely under our control. And so if there is right now, I'm not talking about algebra of numbers, then algebras and numbers are what are they? They're labels. Okay, so just like what is your social security number? It's a label, basically. Your name, first name, second name, for first last name, is a label of you, so that you can distinguish one person from another. Social security is just works better, but once again, it's really a number, right? So it doesn't make sense to do algebra with those numbers, or is it more like a label literally? So they just as well made some. Instead of going 1 to 3, they go alpha, beta, gamma, and it would be still just as good way to separate them. So and that's the same set. So the order of things doesn't matter. And so, for example, if we were to go with lists, then as you can see, we start with a list of students, list of numbers, planets. There's they come in some kind of natural order, but really, if we rearrange them, it's still the same set. Okay, so that's the point. That's the point. They're literally these sets that in the first list and the second list, even though they look differently, they're the same. Yeah, question. Oh, okay. So we even if these are numbers, we just imagine once again they are being in a bag, and we just shake the bag, and that's all there is. Okay, so the order, everything is. So that allows us to treat these sets as sets, and in fact you can do algebra with sets later on. This needs to be addressed in the plain language English language set. It refers to a set of silverware that actually is in a box, and we are then to create a set. Mathematically speaking, we put that set, open it into a bag, and shake that bag again. So once again, to get rid of any structure that might be present. Okay, so just to make, you don't have to do it, but because the set on the left and the set on the right is the same thing, mathematically speaking. But once again, remember there is no structure. So the fact that there's a mold there, and you can the fork is next to the knife, for example. Okay, so that is the structure. That is the order of things that in the box, and we get rid of it. Okay, in the set. There is no order. So just as well, if you were doing some fancy dining, then once again the silverware is arranged particularly around the table, and once again that would be a set in the not in the way we think, but rather in mathematics, but rather in some kind of a way outside of mathematics. Inside of mathematics, it's a bag. Okay. Okay, so all right, so it is not another definition that unlike just about everything in mathematics, we try to define everything specifically beyond any doubt. But the certain things are we do not try to define it, such as we don't say what you remember. This is the limit, this is the derivative, this is the intersection, or whatever. All can be defined very precisely, but with the set, we do not do it because it's such a basic idea that it would be just will take us too far into the depths of the foundations of mathematics and logic and all of that, and how to deal with that. That we're not trying to do that in this course. Okay, so the explicit list of elements of a set gives you a set. That's very easy. There's a beginning and the end. That's very the most convenient way. But in mathematics, the sets are frequently infinite. Okay, so here I had to deal with that idea by putting dot there. You know that there's a pattern and continues on indefinitely. Okay, so but still, because the pattern is visible, so we know what it is. But it's more common actually to have in mathematics define sets by conditions, which we had just did last time. Remember, we had points, xy points that satisfy those conditions. Conditions in order to produce that blend of coffee that we consider acceptable. Okay, so for example, that's what we would like xy with x plus y is equal to 6, because your blend has to be 6 pounds altogether. So any combination of the two types of coffee has to add up to 6, and that is a condition. Okay, so then we define those pairs of numbers, which are also points on the plane. We impose a restriction like this on them, and that creates a set. Okay, so it is an implicit definition of a set rather than explicit, which when you have a list. So list is uncommon, and ideally sometimes you have a condition and you work out and make it explicit. So that's frequently what solving mathematical problems is. You define something that you want to accomplish, achieve, or find. Okay, so such as that perfect blend of coffee, and then you simplify, and at the end it is very explicit. So you remember to solve the problem with somewhere. If not, then we have 2x plus 3y is equal to 14. So this is the set defined by two conditions. Yeah. You don't have to raise your hand. You just speak out. Yeah.
Okay. What is implicit versus explicit again?
The restriction, explicit is a list. Okay, ideally. And remember, so we started with this. Remember last time we were solving the problem, the basic linear problem, linear algebra problem of finding that blend of two types of coffee. We translated into mathematics, which was basically this. Those pairs x, y that satisfy these two conditions. So it was a pure translation before we would start solving the problem. We translated into mathematics. And so our requirements are implicit, because, well, all the requirements are basically implicit. So that's what you want to get. Explicit is that there is no requirement. It is a explicitly point out this is the answer. Remember, so we solved. So this is implicit. And explicit, remember what the answer was? We examined the graphs and we ended up with 4-2. That's explicit. You realize it's the same set, right? Given on the left with these conditions, restrictions to be satisfied, and on the right it is a literally a list of one element. 1 point in the whole plane satisfies these two conditions. No, there is remember we tweaked it. Go back. We tweaked the condition in such a way. Remember these two? I changed the condition slightly. I replaced 3 with 2 over there. Okay, so I ended up with 2 lines that produce nothing. Okay, because there is no x, y that satisfy both of these conditions. Over here, I tweaked it a little bit more, and then turns out there are infinitely many solutions. Okay, so this I did not solve this problem in the sense how do you represent it explicitly. When there are infinitely many answers, explicit is not easy to produce because there is the list would be infinite. This is not even a list. Okay, so the dots look like a list, but the reality is because it's more than a list because all the points in between are also part of the answer. So it's not always working out that way, but ideally is it every problem that you might bring from real life you really want to, even though it's it's impossible to have one single answer. Okay, so your conditions that you have may be 100. At the end, there's one single answer if you're lucky.
Okay, so could you think of implicit as like the problem and explicit as the answer? Or
Yes. Yes.
Okay.
Yeah. So yeah, so explicit is probably the if it is explicit, then probably there's for example, there's only one way to do it. Probably. Yeah. While you can rewrite the implicit in them. Okay, so conditions once again. These are conditions. We take we take the sets that have had. Okay, and then you can impose the conditions on those lists. For example, students with if from our list with an A. Okay, and then we have all the numbers what we concentrate on even numbers only. We look at the planets, but then look at the planets that the name of which starts with an M. Okay, so all of these are then create sets by imposing once again the conditions on them. I do have an explicit list of all students in the class, but I do not have a list of this, right? No list. And that would be the question, what is, and the solution would produce a list if we are once again do our work here or put work in, and then it will produce a list at the end. Similarly, if you have numbers, you can try to list even numbers, even though even numbers are described implicitly. What's an even number?
Divisible by 2.
Divisible by 2. So I'm saying, well, let's pick all the numbers that are divisible by 2. And you describe all of them, but you don't have a list. Okay, so you describe, once again, the third one, description of planets that start with an M. Once again, it is a condition, but we don't have a list. You have to work then to actually produce that list if it at all possible. The point is, of course, that we have created a set nonetheless, even though there is no list, and but the set is there. Okay, so then you can modify, and if necessary, you can turn it, if all possible, you turn it into a list, and then you're done. You solve the problem. So in geometry, these are sets. In geometry, especially in Euclidean geometry, you draw circles, triangles, lines, and they are made of what? They're made of dots, of points. So the points are then the elements of that set. And the point is this picture is especially revealing is what is that this how the set is defined. The condition that was put on the set has to be explicit enough and make sense enough so that we can tell every time does the point belong or does not belong to the set. Okay, so the purple one does not belong to the line, you can see, and the red one does. Okay, so similarly here you can test every student and look at him and look at the what the grade is and then put it on the list or not put it on the list. That's how we solve the problem. Similarly, look at the list of all the planets and pick one with M. And once again, if it's Mars, yes, in Earth, no. Okay, so every time. So that's what defines a set is that when we are able to do it. Okay, so without actually solving the problem, we look at the condition and make sure that it makes sense and it does filter, if you like, all the possible elements into two yes and no. Okay. So this is what might happen if you try to define sets that the conditions are too vague or nonsensical. Then you're not creating sets because it is ultimately it is X and then some kind of question, and there is then yes, and there's a no, and there is no third possibility. then so the yes, this will be the set. So that question defines a condition or restriction or a bunch of them, and then every yes will produce the element of a set, and then every no will produce element that something else. Hypothetical. You're building this machine, you don't really run it. So. Okay, so another running example are these boys that I to illustrate the most immediate ideas about sets and functions. Once again, there, as you can see, there are 5 of them. Okay, so they are distinguishable, so all different. But nonetheless, they are not related to each other. There is no order to them. There is no closeness to them. There is no friendship. Nothing like that is discussed. You can distinguish them, by the way, by their names, tags, by their color their t-shirts or color their hair. That doesn't matter. So it's just different ways to emphasize the point. They're unique. They're individuals. Okay. So, but otherwise, you can rearrange them. That's what the pictures are in the middle on the right. You can rearrange them, and that's still the same set. And then you can put them as a list. Okay, you can put them on the list vertically if it's a spreadsheet. You can put it in a row, but mathematically, this is what notation that we use. We use braces in the beginning and the end. Okay, so once again, and this is, look at it, this is the equal sign over here, which is certainly important in places like algebra, but this is even when we speak of sets, equal sign makes sense. So once again, I rearrange the items within the list. It's the same list. It's the same. So it's not a list technically. The list has an order and the set does not. So from the point of view of computing, I guess we should be careful about it. So list might be assumed might have an order. Might, what am I saying here? Might be ordered. So when I say a list, it is the answer rather than the question. So remember, the list is really not it, because once again in computing, list is a fixed order, and so it takes actual work to rearrange the terms. In mathematics, we just say, oh, it's the same thing, and not worry about it. Okay.
So lists are sets. Sets aren't necessarily lists because lists can be ordered and sets cannot be.
No, a list, I think, as I understand what the meaning of list in computing is that it is an order. All of these are lists, right? And they're, as lists, they're different. Okay, so different lists, same sets. That's the equal sign. Okay, so as lists they're different, as sets they're the same. Yeah.
Elaborate things about sets is you can't have duplicates. That's
right.
That's one of the properties of sets. There's nothing that's duplicated in a list. You could have something.
Right. So well, that would be okay. That's a good point too. That a list might have repetitions. Okay. So in the set, if you do have repetitions in the set, you better remove them to make that clear. So so for example, if we start counting them, they will be discounted. So if you start counting, you better throw them out. Okay, so this is the terminology. Tom belongs to X. If I name the set, which is what I did right here, name the set X, then Tom belongs to X, so X contains Tom, and so on. So all of these things are then available. This is once again the next line. I'm making the point of the equal sign that emerges in algebra over here, but then among sets, it's also it can be equal to, and once again rearranging the order of things produces the same set, and so they're equal to each other. Okay, so for example, if you're solving equation x squared is equal to 1 and you solve it, producing what we call a solution set, or the solution set. Okay, so x squared plus 1, solve it. What does it mean? You're supposed to produce the solution set. Which one of the two the answer? -1, 1, or 1, -1. Doesn't matter. It's the same set. Okay. That's what it means to solve an equation, is to produce the solution set, meaning that every single number in the set is a solution, and secondly, you did not miss any. So that's what equal sets are. If you want to do it, that definition of two equal sets in a manner that is seems to be a little bit overdoing it, but that's if you want to be precise. So that's how it is. If element of x, every element of x belongs to y, and every element of y also belongs to x, then these are the two identical sets, and we just could say just they are equal to each other, and we use the equal sign justifiable. Repetitions are not allowed. Remove them beforehand. And so here Ben, and I remove one of the Bens because then on the left you better not have it. If you're writing it in the form of a list, your list should rather not have repetitions. So in other words, what just the point was made. Once again, different lists, same sets. Even though the one on the left is not the way we do it. We don't write sets with repetitions and just say that it's okay. It's not, but that's sometimes happens. Okay, subsets. It's the sets within sets. Okay, so here I take my 5 element set of boys, and I could go with 1, 2, 3, 4, and 5 or sizes for subsets, and then I can create a bunch of them. Once again, if you're into that kind of thing, you can try to count in how many ways you can do that. For example, you can do 1 element subsets. There are 5 of them. How many 2 element subsets? Well, we can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, I think the answer is 12 probably. But you can figure it out. It's really not a part of this course, but in computing, and like if you were to take any kind of finite mathematics course related to computing, then counting the number of elements in a set is a big deal. Why? Why is it important to count number of elements in the set? What?
Very open question.
Well, it is an open question, but can you think of an example why counting the number?
Memory allocations, the first thing to come to mind. That's one of the big things. Like if you're gonna download like a software or something like that, space is one of the big things.
Yeah, but there's a much more immediate, practical question why we might be interested in counting is a probability. So you might be interested in what's the likelihood. We have 5 boys. We have, well, that example usually have like a team basketball team, and you have 20 players, but you on the field on the court you have only 5. So what's the likelihood that a particular person will be on the team on the field rather? So then what do? You count the number of possible teams. And what's the likelihood, which will be a subset, the teams containing that particular person will be a subset of teams altogether, and then you relative size of those teams with that person in those teams will be proportional to the total number of possibilities will produce the likelihood to be on the field. Okay, if it makes sense. So that doesn't matter right now, but it is the why set theory is important in everywhere, and in calculus does come up as much because there's so much stuff going on. But whether you're doing linear algebra or you're doing, say, probability, sets are very important because of this. It's you have to be very explicit because at some point you will be doing counting, and counting is whether or not you just know how large it is, or you're computing probabilities. Once again, proportions. You need to know the size of the set and the size of the subset. Okay, so that's all I want to say about that. So once again, a subset is every element of A is an element of X. That's what makes it subset. Once again, here I picked a few, so I have 5 boys, and then I form K, which consists of 1 boy, and so that's T, but A contains 2 boys, and the set Q, once again, giving names. If we give names, remember, algebra, you give names to numbers that you don't know or do know, and same with sets or subsets. So just to distinguish one from the other, you give it a name. So Q contains of those 3 boys. Okay. All right. So notation. Okay. So which resembles the notation of less than, because in the context of lists, especially, the subset is always smaller or equal to the size of the set. Okay, the set is subset of itself, to be clear, but it cannot be larger. So that's why there is a match. There is a match, and because if it is a proper subset, as we say, so proper subset is when A is not equal to X. Okay, then it is strictly smaller in size than the larger set. Okay, so that's why it matches, even though when sets are infinite, then you can have a smaller subset with the same number of elements. Again, geometry, subset of a line is a segment. The subset of a circle as a curve, it is maybe an arc. And the subset of a triangle could be a circle inside the triangle, and so on. So these are very easy to illustrate with the idea of subsets if it is actually geometrical. Okay. The empty set. Okay. So this is a list with nothing in it. Yeah, so let's be clear. List. Because it is if you can represent it as a list, you do, because that's actually explicit, to be clear. So there is no condition that to be verified. You just have a list and it has nothing in it. Okay. So just like it takes time to get used to it, just like with the 0, if in history it was a controversial to have a number which has no magnitude. Okay, so and that's a 0. And we're in a similar place. So a set that contains no elements doesn't even make sense to discuss it, but it does. Just like, remember once again the question of producing a blend with a particular price, that it is impossible. Particular price and weight is impossible, and that's the impossibility. It is a set, but because how do we express mathematically the fact that it is impossible to create such a blend? And the answer is the set of these blends that satisfies those requirements is empty. Okay. So that's the notation crossed out 0. A couple of words about nomenclature of the numbers that we have. Natural numbers, and stands for it. Usually, okay, so natural numbers, everybody knows natural numbers. Do we include 0 or do not? We do not. That's a big controversy in mathematics. Do natural numbers include 0 or not? Anybody has an opinion? So yes. Yeah, as you can see, I think yes, and it's more convenient to start counting with 0, even though that's the point of natural numbers is counting. Do you include 0? And I think you should. Okay, so but some say you shouldn't. What?
Because I think 0 is considered like positive.
Well, it's not positive. 0 is not positive.
It's
not. No, yeah, positive starts with 1. Technically, so that's why you have to sometimes say non-negative, which is very awkward, but that's what happens. Be positive.
Yeah, imagine.
It would make sense to start counting with 0, because in the same likelihood you could have something, you could have nothing. Like say if you had an apple, it's taken away, now you have 0 apples. Yeah.
Right. So count those cows, and then you count the cows in your herd. Okay, start counting, and I don't have any cows. Okay, so what's the answer? There is an answer. If you want to give an answer in a mathematical sense, you'd better have something there that's not a whole sentence that you have to write out. And in a similar fashion, you introduce negative numbers. So once again, if you are yeah, so you're gaining or you're losing, and when you're losing, you might have negative numbers as well. So yeah, so it's a whole history there. But this is, by the way, is you can think of integers as milestones on the road, and then you want to have, you know, instead of speaking of going west and going east, 1 mile at a time, then and having a mark. So this could be 1 east, 2 east, and this is 1 west and 2 west. So that would be normally how we would approach it probably. But if you want to mathematical, if these are labels, right? So if these are just labels, then you can just as well have them. That doesn't matter what they are. But if we already have integers available as a set that we understand well, then just label with negative numbers as well. Or you can think about, you know, if it's about money, then you gain money, you lose money. So on the left you have credit or debt to express negative numbers with. Okay, so it's also was controversial at some point. Is that do negative numbers have a meaning? So, but ultimately we accept that. So why do we need? So okay, so I skipped rational numbers for some reason. What are rational numbers? Rational numbers. An example idea for what a rational number is. What? Okay, that would be, but what about infinitely many threes? Rational. Infinitely many nines. Is it rational? What is everybody has had calculus 1 right here. So what's 0.999 with infinitely many nines? What is it? What? It is 1. Yes. In fact, it's an integer. So the point I'm making is that the decimal representation is not really an indication. Rational numbers are fractions. That's it. Fractions of integers. Okay, and so once again, I don't want to go into history, but that's how things progress from natural numbers to integers to rational numbers to real numbers. Okay, and so fractions. So why do we need real numbers? Why do we need real numbers in comparison to fractions? The picture somewhere. This is how fractions might work. As a matter of fact, imagine the carpenter's tape, and it has inches, that half inch, quarter inch, and hypothetically you can keep inserting points infinitely many times, and every time you have a fraction. So fractions could produce any accuracy you want. Okay, so and yet we say, well, that's not good enough, and we invent real numbers. If you're familiar with the history, how it actually happened, because there are irrational numbers that are nonetheless real. So not rational, irrational. An example of a rational number.
Rational would be like pi, or irrational.
Rational is 5, irrational.
Pi.
No. No, integers are integers. Fractions of integers are still so all integers are also fractions. So anybody knows an irrational number? No. Well, so well, it was a big deal at some point a long time ago. The Pythagoreans was it called? And they thought everything was rational, which has nothing to do with rationality, by the way. Rational means ratio. Fraction. In other words, for fraction is ratio, and that's so everything, integers are, and the rational numbers come from the gods, and there is nothing else. And then they discovered what they discover using, not coincidentally, the Pythagorean theorem. What did they discover?
Square root of 2.
Square root of 2 is the diagonal is, if x is the diagonal of a 1 by 1 square, then x squared is equal to 1. So x squared is equal to 2. Okay, and they were also going on they, but some particular person among the Pythagoreans proved that no, x is not rational.
Said cult.
In a way, they thought they have mathematics, geometry ruled everything, and yeah. Oh, the punchline is they made that person commit suicide.
The punchline is.
It is, but yeah, so if you now don't believe that it was a cult, then yeah, it is, as the story goes. They proved that their theory was all wrong, their religion was wrong. That not everything is rational, and he demonstrated mathematically that if x squared is equal to 2, that number cannot be rational. So everything went crumbling down, and yeah, so I don't know exactly how it happened, but it wasn't with them anymore shortly after. So, okay, so a number, it is a real thing. A diagonal of a square is a real thing, and yet it is not rational. So that's why we need rational numbers, progress from rational numbers to some other numbers that would take care of these gaps. So there are really no gaps among rational numbers. They're totally dense. You cannot just say, well, there is one rational number, this is another one, and there are no rational numbers in between. You can always insert another one. But it just happens that there are still missing number, and there are infinitely many of them. So if the square root of 2 is not rational, then square root of 3 as well, and square root of 5, and so on. The irrational numbers are everywhere. And imagine that if one number, where's the square root of 2 is here somewhere. Okay, so imagine that's missing. It's not only geometry matters. Imagine that this rope, this missing a point. Okay, one point is missing. One. So these are numbers, okay, and one number is missing. What's going to happen? It's not connected, then it will fall. Okay, so the way we think about the world around us, we think that's there, it is intact, right? So every point is there, and so that's why we want real numbers to represent reality. There are no gaps, no cuts. So if you cut it, it's not intact, or it doesn't hold anything. So at least that was a simplified. So they were not thinking in terms of atoms and so on. So that's we were building like a mathematical. They were a mathematical model of the world surrounding them, and then so you don't want missing numbers, and so they ended up with real numbers. And we don't do a lot of rational numbers, but we just assume everything that we're dealing with is a rational number. So for example, locations we are not missing as they are moving through space. There are no missing points. I don't know, temperature, pressure, whatever numbers you can think of, they are all real numbers with no missing values. So that's why calculus is so hard to apply, and that's the calculus built upon that. But every time you're dealing with something incremental, you might have a problem. So for example, population modeling, there is no such thing as square root of 2 people. But if you want to model population, then you assume that they change continuously. Okay, so well, it's a trade-off.
So is pi like
Pi is also irrational. Yes.
irrational? Okay.
Pi
I think that's what I was
irrational,
trying to say
E is
earlier.
irrational, but those are worse than that. They're transcendental. So even among irrational numbers, there are transcendental numbers. Irrational is simply not rational, not fractions, but transcendentals are the ones that there's an equation. Look at very simple equation: x squared is equal to 2. and its solution is irrational. But what if, is it possible that every number that is irrational is represented, is a solution to such an equation? The answer is no. So they would call them algebraic. So x squared, it's an algebraic equation, and its solution is called an algebraic number, and but that's not it. Pi is not a solution to any algebraic equation. Okay, so even more weird things are there, within the real line. Nothing else. Yeah.
Are imaginary numbers considered irrational or?
Well, it's a good question, but you can have, it depends on where you're building from. You can build complex numbers with nothing but integers. Okay, because it's basically two directions, and you can have a real part. There are real and imaginary parts. We'll talk about that later, and then you can just make the real part integer part, and the imaginary part also made of only of integers. So it is possible to have an alternative theory. Usually we assume that they are real, well, this real and that real, but you can do it with integers and rational numbers as well, just as good. So we'll get to that later. This is the hierarchy. So n is a subset of z, z is a subset of q that I skipped, and then q is a subset of r. Okay, so whichever is necessary, we use that. The more specific one in calculus, you might remember that it was primarily these two. R is for example, the inputs and outputs are usually real numbers, except for sequences, in which case the input is a natural number usually. Okay, so sequence starts at some point. You can start counting. All right. Okay, next is once again, let's quickly review what it looks like. The natural numbers from 0, the integers has two infinities. That's the main difference between natural numbers and integers. We have two infinities, one or the other. But there are still gaps. So if you start, you could sort of think about once again about the carpenter. And does he really need fractions? He could operate in terms of like half an inch every time. So it's just which one of the markings on the tape you pick. You can do it with inches. You can have half inches. And in either case, you are dealing with integer arithmetic. So do you really have to, for example, do 1/2 plus 1/3? Maybe not. So you can just entirely stick to half inches and be happy with it. And then if you need more accuracy, go to 1/4 of an inch and so on. So integer arithmetic actually is very, very powerful. So because it is an integer arithmetic could be applied to different units. Remember the metric system, they do the same what I just explained, half and half and half. The imperial system, inch, half inch, quarter inch. But you can insert 10, right? That's the metric system, and they have a word for everything. So you have a meter, decimeter, centimeter, millimeter, micrometer, and I forgot these, like 20 of them. And then you can go in the other direction as well. So every time you can make it units bigger and smaller just for your own convenience, and you're still doing nothing but integers. Okay, whether we do it infinitely long a number of times, that's we do it in calculus, and we just assume that we have already done it, and then we have real number line, and no missing points are there. So imagine, by the way, missing point. If you were to have missing point, how those two lines intersect? You know, remember we talked about how do you know that two lines intersect, and the answer is, well, they intersect unless they're parallel, but if in those lines points are missing, there might be actually no intersection whatsoever. So once again, it is just does not match our how we see the world around us. Okay, so closer and closer. Insert either we insert those points, or we just zoom in and see more and more possible locations there, and everything still remains an integer. But if that crosses infinite, then we filled in the real line, and so it is totally intact, like a rope that can hold things. Yeah, that's inserting different stages. Metric ruler, when we insert 10, these are representations of rational or irrational numbers. So the first two are rational. Pi is irrational, and that's why we need calculus in order to be able to approximate irrational numbers, because we don't have a choice. for those bunch of threes, we know it's 1/3, so there's a compact representation of that. But if we were to speak of pi, we don't have a choice but to approximate it, and that's why we need a decimal system, and that's why one of the reasons why we need calculus. Okay, what we assume that we've done all the calculus part, and so all the numbers are now available. So that's the line. Let me build the coordinate system for the line. This is the line first. Okay, then I put an arrow on it to have direction. Okay, so that will be the positive direction. Then the opposite will be negative. I insert the origin. Okay, from which I start counting, or rather measuring, not counting anymore. And then I choose the unit of length. And then I start measuring to the left and to the right. And I insert like milestones on my line. And then the end, this is the end result, with possibility that if necessary, I could subdivide these intervals into smaller pieces if necessary. But otherwise, this is my axis, and each number represents a coordinate. And once again, they are not shown, but you can find the coordinate for every point on this line if necessary. So whether it is 1/2, or it is pi, or it is anything else, it's all there taken care of. And once again, built in these 6 steps. Okay, so depending on what the building blocks is, you might produce either like a missing point if you are going with the unfinished business, and the only insert, I don't know, 5, 10, 20 times and then stop. Or if you do it into many steps, then it's made up like domino pieces. So once again, there are no gaps, and it is this solid line. Solid line, you like a solid line, or you look a line, and prefer a line with markings on it. It doesn't matter which one is better. Okay, so we just talked about completeness. This is how the coordinate system works. So every location on the line is a number, and but conversely, every number has a location on the line. Okay, so all of this is familiar from pre-calculus, but we're just quickly reviewing it. Locations and numbers are pretty much the same. But by a number, we always mean a real number in this context. Okay, so that's a visual model of real numbers that we go to whenever we need to visualize things. All lines are they're not missing any pieces there. Okay, so another way to visualize numbers is colors. Okay, so in this particular case, I just went with Excel, and so you can just it's called conditional formatting in Excel. And so depending on what number is contained in the cell, it colored differently. So on the usually you see what's at the bottom, which is mathematically it works fine, right? So negative numbers are blue and positive are red. But to make a better point, mathematically, is the intensity of the color is at the top. Okay, so the small numbers are always one is white, and larger numbers are black. That's how the digital images are made, right? So it's nothing but an array of numbers and a grayscale image, right? So then once again, zeros are white. Hold on, or is it the opposite? 0 is white, or 0 is the 256. Anyone have dealt with the digital images?
I want to say 256 is white.
Yeah, I think so too. Yeah, so 256 is white, and white is black. So that's the format. Mathematically speaking, makes no difference, but the reality is it's actually, yes, I think 256 is white, or 255 is it, and the 0 is black. Oh, and the numbers are changing from left to right. When you have different colors, that's what? RGB, 3 coordinates different. So we're not doing that right now. So if we're looking at real numbers, we can represent and we can understand grayscale images, but not color images. Okay, so another reason to study multidimensionality and multidimensional spaces is once again representing it is a color space, if you like. Okay, so we'll get to that later. Relations and functions. So here I pick another set, and we already had a relation. So let me remind you, this is a relation. Oh, we had 6 here. Okay, so there are 2 sets, x's and y's, and they somehow required to be related to each other. And here, in a more specific way, I'm establishing a relation between 2 sets. And so this first set we already had, that was the voice. with 5 boys now have four balls, reflecting the games they like to play. And so once again, it is a list. The list can be rearranged. It's the same set. And now the two sets are not related to each other in any way, but you can create that relation by just talking to the boys and ask them what they like to play. And that way, Tom likes basketball, which means that we might draw an arrow. Okay. On the other hand, so I draw an arrow from Tom to the ball, but on the other hand, I could, if I talk to the boys, I draw this curve on this arrow. On the other hand, what if I alternatively instead of examine the balls and ask ourselves what boys played with that ball, and so then I would have actually go with the arrow going backwards. Okay, so the relation between the boy and the ball, in this case Tom and basketball, is actually two-ended at this point. There is no, we're not starting with the boys and going to the balls or balls to the boys. It's the same thing. Okay, the relation is two-ended, and here's have a bunch of two-ended arrows connecting a boy with the game that he likes to play, which is maybe several. As you can see, there are several. Some boys like more than one game. Okay, you can see the basketball and tennis over there. And same with balls. Okay, some of them played with more than one boy. And then, and thirdly, you notice something else there. Look at Ned. Okay. So I didn't mean to. Yeah, I didn't mean to suggest that with the name, but it is interesting. Yeah, a slip. Okay, so doesn't like to play games at all. So it is still totally all right. Totally all right for a relation to have no errors whatsoever. One person has, or one ball is not played with by anyone, or one person that doesn't like to play. That's all fine just as well. So once again, we go backwards and forwards. So what creates a relation is a list of pairs, really. At the end of the day, we pair up a boy with the game, and every game with the boy, and then as you can see, there are 6 arrows and there are 6 pairs. Okay, so that's what a relation by definition is. It is a set of pairs. We have two set X and set Y, and then we create a set of pairs, which could be, in this case, it's finite, only 6 elements. Well, say 6 elements in that set, but nonetheless, you could have infinitely many of them. We visualize, just like we visualize sets as some kind of blobs. We can visualize relations by a bunch of arrows between 2 sets. Okay, so how else? So that's the once again is the yes or no question. We take a pair boys and ball, and then ask the question: Does the boy like the ball or the game? If it's true, they are related, and we put a cross next to it. Or if it is they are not related, we do not do it. So the result is we can actually do a table. So the table would be once again Tom. What is it? Yeah, Tom and basketball. So I put a cross here, and then I could continue on, and there will be 6 crosses. These are the 6 crosses, and so it's a table with the rows responsible, 1 row per boy and 1 column per ball. Okay, so there are six crosses in it. Of course, there is no difference between what's on the left and on the right. Data-wise, once again, doesn't matter which one comes first. It's really the same amount of data. So the relation can be represented with arrows, or it can be presented by tables, and either one of these tables is totally acceptable. Okay, so it is frequently how data is handled in a kind of a simplified situations. You can just literally, if you have a group of boys and you want to know more than just 5, and then you want to know which ones plays what, you create a table like this and put a bunch of crosses there. So quickly to find out if you need to form a football team, you will right away know who will go into that team, right, like this. Okay, so if we apply the same idea to numbers, we end up with the graph. Remember the graph, where we get that big graph from pre-calculus and use so much in calculus, is in fact nothing but just putting crosses on those x and y that are related to each other. Okay, so it makes no difference. Just in the case of when you do it in calculus, you usually put a dot, and then you hope that when you put enough dots, what might happen to those dots. If you have a bunch of them, what do you expect to happen? In a calculus context. No, what I meant is, so instead of having, well, when you have data, then these are just points that's scattered around the table, and so they may have nothing to do with each other. But if you were in the calculus context, you probably will end up with a curve. Okay, x's and y's, they're related to each other by possibly some hidden physical phenomenon, and then the relation might actually be, if you sampled enough times, produce a curve. Okay, but once again, it is, where does it come from? It comes from the same place, a relation between two types of data, maybe time and location, for example, or time and location like this. And then if there's a kind of motion, then there is, it, once again, it visits every point between two locations. So if you were, what you're doing here, you pick locations in moments of time, X and Y, you pair them up and ask yourself, was I there ever? And if you were, then you put a dot there. If you put enough dots, you might end up with a curve. Literally, if you do it with Excel, it's simply points become so close to each other, they become indistinguishable. Okay, so before I didn't we do it last time, or quickly show you that Excel, unless it was another class. So I'm not sure how familiar you are with Excel, but probably you should. A bunch of dots, a bunch of pairs of numbers right here, and then you highlight them like this and press insert chart. Okay, and so naturally you end up with a bunch of points, but if you had more points, these points will produce a curve. Okay, I'll stop here. Class Smith, if you have a question.